Right now, you are absolutely certain of something. You are certain that the Andromeda galaxy is about 2.5 million light years away. You are certain that the nearest star is 4 light years away. You are certain that distance is one of the most basic facts about reality. Things are either close or far. Space is the stage. Objects sit on that stage at measurable separations. That feels undeniable. But I want you to slow down and ask a question that sounds almost stupid. What exactly do you mean by away? When you say something is far, what are you actually measuring? A number on a ruler, a signal delay, the time light takes to arrive, a coordinate difference in a model. Already, without noticing, you have mixed geometry, time, motion, and assumptions about the structure of the universe into a single, everyday word. Distance feels fundamental because your brain evolved to navigate meters, not galaxies. For survival, close and far had to be stable concepts. But physics does not care about what feels obvious. Physics cares about what survives under extreme conditions. And when you push the idea of distance to its limits, high speeds, strong gravity, quantum scales, something shocking happens. It starts to dissolve. By the end of this journey, you will see that distance is not an absolute backdrop against which reality unfolds. It is not a fixed grid that the universe is built upon. It is a description that depends on motion, on gravity, on perspective, and perhaps most disturbingly, on quantum relationships that do not even speak the language of space. The universe is not simply vast, it is stranger than that. When astronomers tell you that the Andromeda galaxy is 2.5 million light years away, it sounds like a clean geometric statement. It sounds like someone stretched a cosmic ruler from here to there and read off the number. But that is not what is happening at all. A light year is not a unit of space in the ordinary sense. It is the distance light travels in 1 year. So when you hear 2.5 million light years, what you are really hearing is this. The light that is hitting your telescope tonight left Andromeda 2.5 million years ago. That is a statement about time. You are not measuring where Andromeda is right now. You are measuring when the light began its journey. You are looking into the past. In fact, every astronomical distance you have ever heard is secretly a time delay dressed up as a length. And here is where it becomes uncomfortable. During those 2.5 million years, Andromeda did not sit still. It moved. The Milky Way moved. The universe itself evolved. So what exactly is the distance you are quoting? Is it the distance the light traveled through expanding space? Is it the distance between the two galaxies when the light was emitted? Is it the distance between them right now according to a particular cosmological model? These are not the same numbers. Cosmologists actually use different definitions for different questions. There is the light travel distance. There is the proper distance at a given cosmic time. There is the comoving distance that factors out expansion. Each one is mathematically precise. Each one is useful. And none of them has a monopoly on being the real one. So when someone asks, how far away is Andromeda? The scientifically honest answer is not a single number. The honest answer is, which definition of distance do you want? Already the idea of distance has cracked. It is not a single absolute fact floating out there in the universe. It is a relationship defined within a model, measured through light, interpreted through assumptions about motion and expansion. You thought distance meant how far something is. But even before relativity enters the story, even before gravity curves space-time, even before quantum mechanics scrambles your intuition, distance has already become a question about time, perspective, and definition. And this is only the first layer. If distance were truly fundamental, then once you defined it carefully, it should settle down into a single observer-independent fact. But it does not. Even after you clean up the cosmological definitions, even after you specify exactly which distance you mean, there is still a deeper problem waiting. Special relativity. In 1905, Einstein did something that sounds abstract but is actually devastating to the idea of absolute distance. He removed the possibility of a universal frame of reference. There is no privileged cosmic grid that defines what is truly at rest. Motion is always relative. And once motion becomes relative, space and time cannot remain rigid. Here is the key result. The length of an object depends on how fast it is moving relative to you. This is not an illusion. It is not a measurement error. It is built into the structure of space-time itself. A ruler moving past you at high speed is shorter along the direction of motion than the same ruler at rest beside you. The faster it moves, the shorter it becomes. This effect is called length contraction, and it has been confirmed experimentally in particle accelerators and high-precision measurement. At everyday speeds, the effect is tiny. At 10% of the speed of light, the contraction is small but measurable. At 90%, the contraction is dramatic. At 99%, distances in the direction of motion shrink to a small fraction of their rest value. Now apply this to something enormous. Imagine you are on a spaceship moving toward Andromeda at 99% of the speed of light. From Earth, someone measures the distance as roughly 2.5 million light years. But from your frame of reference, that distance is contracted. It is not 2.5 million light years for you. It is dramatically shorter. Both measurements are correct. There is no deeper hidden number that both of you are approximating. The distance depends on the state of motion of the observer. Change the velocity, change the geometry of space-time slicing, change the distance. So what is the true distance between the Milky Way and Andromeda? There is no answer independent of a reference frame. Distance is not something sitting out there waiting to be discovered in its pure form. It is something that emerges from how space-time is structured relative to motion. The universe does not provide a single ruler that everyone must agree on. It provides relationships that depend on how you move through it. And if motion can reshape distance, then distance is not an absolute backdrop. It is a feature of perspective embedded in the fabric of space-time itself. If special relativity cracked the idea of absolute distance, general relativity shatters the stage completely. Up to this point, you might still imagine that there is some kind of flexible grid. It stretches. When you move fast, fine, but at least there is still a background arena called space, a place where events happen, a container that holds galaxies and stars. General relativity removes even that comfort. In Einstein's 1915 theory, space is not a passive stage. It is dynamical. It bends. It stretches. It responds to matter and energy. Mass does not sit inside space the way a bowling ball sits on a mattress. Mass tells space-time how to curve, and space-time tells matter how to move. And here's the crucial point. Distance is defined by geometry. If geometry changes, distance changes. Near a massive object like a star, space-time is slightly curved. Near a neutron star, it is severely curved. Near a black hole, it is curved to an extreme. The shortest path between 2 points is no longer what your Euclidean intuition would call a straight line. It is a geodesic, a path determined by the curvature of space-time itself. That means the distance between 2 points is not a fixed background number. It depends on the distribution of mass and energy around them. Change the mass distribution and you change the geometry. Change the geometry and you change the distance. Even more unsettling, the coordinates we use to label space-time points are not physically sacred. You can choose different coordinate systems to describe the same physical situation, and what looks like a large distance in one coordinate system can look much smaller in another. The physics does not depend on your labels. The geometry does. Inside a black hole, this becomes almost impossible to visualize. From the outside, a black hole has a finite radius defined by its event horizon. But the interior geometry is radically different from flat space. The way distances behave inside depends on how you slice space-time into space and time. Different slices can assign very different spatial distances between the horizon and deeper regions. The lesson is not that space is an illusion in some mystical sense. The lesson is that distance is a property of geometry, and geometry is a physical field shaped by matter and energy. There is no rigid cosmic ruler. There is no universal measuring tape laid down before the universe began. Distance is not the foundation on which physics sits. It is part of the physics itself. And if distance depends on motion in special relativity and depends on curvature in general relativity, then we are already far from the naive idea that space is a fixed, empty container with absolute separations. But we have not yet reached the deepest level, because everything so far has still assumed that space-time, curved or not, is fundamental. Quantum mechanics is about to challenge even that. Now we arrive at the point where intuition begins to fail completely. Quantum mechanics does not just tweak space. It questions whether space is the right language at all. In classical physics, two objects are either near or far. If they are next to each other, they can interact strongly. If they are separated by light years, their interaction is weak or negligible. Spatial proximity and physical connection go together. Quantum mechanics breaks that link. When two particles interact in the right way, they can become entangled. After that interaction, you can separate them by a meter, a kilometer, or a billion light years. It does not matter. They are no longer described by two independent states. They are described by one combined quantum state. Measure one, and the outcome of the other is correlated instantly, no matter how far apart they are. This does not allow faster than light communication. You cannot send a message this way. But something deeper is happening. The mathematical object that describes the pair does not factor into two pieces, one here and one there. It is a single structure spanning what you call space. From the perspective of geometry, the particles are far apart. From the perspective of the quantum state, they are parts of one system. That means there are two different notions of closeness. There is spatial closeness measured in meters and light years, and there is quantum closeness measured by entanglement. Two particles can be touching in space and yet be completely independent quantum systems. Two particles can be separated by cosmic distances and yet form a single inseparable quantum state. So which one captures reality more fundamentally? If you strip away rulers, coordinates, and classical trajectories, what remains is the quantum state, and that state encodes relationships that do not depend on spatial separation in the way classical intuition demands. Einstein famously disliked this. He called it spooky action at a distance. He believed that spatial separation should guarantee independence, but decades of experiments have confirmed that entanglement is real. Nature does not respect classical separability. This forces a radical possibility. Maybe spatial distance is not the deepest way to talk about separation. Maybe what really matters is how strongly parts of the universe are entangled with each other. Maybe what you call far and near are just emergent shadows of deeper quantum relationships. Up to now, distance has already depended on motion and curvature. Quantum mechanics suggests it might depend on something even stranger. Not where things are, but how they are connected. If entanglement hints that spatial separation is not fundamental, holography turns that hint into a mathematical statement. In 1997, Juan Maldacena discovered something that reshaped theoretical physics. He showed that a theory of gravity living in a curved space-time with an extra spatial dimension can be exactly equivalent to a quantum field theory with no gravity living on the lower dimensional boundary of that space-time. This relationship is known as the ADS-CFT correspondence. Two completely different descriptions, one with gravity and curved space, one without gravity, defined on a boundary with fewer dimensions. Yet they describe the same physical reality. This is not an analogy. It is not poetic language. It is a precise mathematical equivalence. Every physical quantity in the gravitational theory has a translation in the boundary quantum theory. Every process in one picture corresponds to a process in the other. Now think about what that means for distance. In the gravitational picture, you have a bulk space-time. Points have positions. There is a radial direction, a sense of depth. You can talk about how far something is from the boundary. You can compute distances along curved geodesics. But in the boundary theory, there is no extra radial dimension. There is no bulk depth in the geometric sense. The boundary theory only knows about fields and their quantum interactions. So where did that extra dimension go? It turns out that what appears as spatial depth in the gravitational description corresponds to energy scale in the boundary theory. High energy processes map to regions near the boundary. Low energy processes map to regions deeper in the bulk. What looks like movement through space in one description is reinterpreted as changing scale in the other. This is a profound shift. The third dimension of space in the bulk is not fundamental in that framework. It emerges from how quantum degrees of freedom are organized across different energy scales. And crucially, the structure of entanglement in the boundary theory determines the geometry of the bulk space-time. Researchers like Mark van Ramsdonk and Brian Swingle have made this connection explicit. They showed that if you mathematically reduce the entanglement between two regions of the boundary theory, the corresponding bulk space-time begins to pull apart. Reduce the entanglement further, and the bulk can split into disconnected pieces. Restore the entanglement, and the geometry reconnects. Space-time connectivity tracks entanglement. Regions that are strongly entangled correspond to regions that are close in the bulk geometry. Regions that are weakly entangled correspond to regions that are far apart. In this framework, distance is not primary. It is a geometric expression of quantum correlations. Remove the entanglement, and space itself falls apart. This does not mean our everyday experience of space is fake. It means that what we call distance may be a large-scale description of something deeper, a network of quantum relationships whose geometry only appears when you zoom out. If that is true, then space is not the container of the universe. It is the shape taken by entanglement when viewed from the inside. If holography suggests that space-time geometry can emerge from entanglement, another bold idea pushes this even further. It is called ER equals EPR. The name sounds cryptic, but it connects two of the strangest concepts in modern physics. ER refers to Einstein-Rosen bridges, what we commonly call wormholes, hypothetical geometric tunnels connecting distant regions of space-time. EPR refers to Einstein-Podolsky-Rosen pairs, entangled quantum particles described in their famous 1935 paper. The conjecture proposed by Maldacena and Leonard Susskind suggests that these two ideas are not separate at all. A wormhole connecting two black holes and a pair of maximally entangled quantum systems may be two descriptions of the same underlying reality. In other words, quantum entanglement and geometric connection could be equivalent languages. Now be careful. This does not mean you can jump through an entangled pair and emerge somewhere else. These wormholes are not traversable. They do not allow faster than light travel or communication. Causality remains intact, but conceptually, something extraordinary is being proposed. When two systems are maximally entangled, there may be a geometric description in which they are connected by a kind of microscopic bridge. The apparent spatial separation between them is a feature of one description. In another description, they are joined through space-time geometry itself. If that picture is even approximately correct, then distance is not the final word on separation. Two regions that look far apart in ordinary space may be directly connected in the deeper quantum geometric structure. What you call empty space between them may not be fundamental emptiness at all. It may be the macroscopic way your perspective represents, a web of microscopic connections. At this point, the narrative has flipped. We started with the idea that space is primary and connections happen across space. Now we are considering the possibility that connections are primary and space is how those connections appear when organized at large scales. The universe might not be a vast container with objects scattered through it. It might be a tightly woven quantum network whose large-scale pattern looks like geometry. And what you experience as millions of light years could be the emergent shadow of entanglement structures that do not themselves contain meters or miles. Distance, in this view, is not the bedrock of reality. It is a translation. Even if you are willing to accept that geometry might emerge from entanglement, you could still hold on to one last comfort. Perhaps space-time, once it emerges, is smooth and continuous all the way down. Perhaps distance, even if not fundamental, can still be divided infinitely. Quantum gravity challenges that assumption as well. One approach, known as loop quantum gravity, suggests that space-time is not a smooth fabric at the smallest scales. Instead, it is composed of discrete quantum units, not points in a continuous grid, but a network of finite elements, sometimes described as spin networks. In this picture, the nodes of the network correspond to tiny quanta of volume. The links between them correspond to quanta of area. Geometry is not infinitely divisible. It comes in units. At scales far larger than the Planck length, about 10 to the minus 35 meters, this discrete structure blends into something that looks continuous. Just as a digital image appears smooth when you step back, space-time appears smooth at macroscopic scales. You can draw straight lines, you can measure distances with arbitrary precision, but zoom in far enough, and the classical idea of a smooth distance between 2 points stops being meaningful. There is no smaller and smaller separation in the ordinary sense. There is a quantum structure whose geometric properties are defined by operators with discrete spectra. This does not mean you can never measure small distances. It means that the concept of distance as a continuously variable background quantity is an approximation. It works extraordinarily well in everyday physics and even in astrophysics, but it may not exist at the deepest level. Think about temperature. You can measure temperature with a thermometer. It feels real. It is predictable. Entire technologies depend on it. But at the microscopic level, temperature is not a fundamental property of a single molecule. It emerges from the statistical behavior of many molecules. Distance could be similar. At large scales, it behaves as if it were continuous and fundamental. At very small scales, it may dissolve into relationships between discrete quantum elements. What looks like a smooth separation between two objects could be the large-scale effect of an underlying network that does not contain distance in the classical sense at all. Now combine this with everything before. Distance depends on motion in special relativity. It depends on curvature in general relativity. It may depend on entanglement in holography. And at the smallest scales, it may not even be continuous. What began as the simplest concept in physics has become layered, conditional, and emergent. And we are still not at the end. Now step back and look at the full picture. At the largest scales, cosmology already forced us to admit that distance is tied to light travel time and to the model of an expanding universe. There was never a single universal number hiding behind the scenes. There were definitions, each suited to a question. At high speeds, special relativity showed that two observers in relative motion do not agree on lengths. There is no master ruler outside the universe that settles the dispute. Distance depends on how you move. In strong gravity, general relativity revealed that geometry itself is dynamical. Mass and energy reshape space-time, and with it, the distances between events. There is no rigid background. The stage bends. Quantum mechanics then split apart the classical link between spatial separation and physical independence. Entangled systems remain unified regardless of how far apart they appear in space. Spatial distance does not fully capture physical connectedness. Holography suggested that geometry might emerge from patterns of entanglement, that what we call depth in space could correspond to scale in a quantum theory without gravity. Connectivity in space-time could reflect quantum correlation. Loop, quantum gravity, and related approaches implied that even the smooth continuity of distance may be an approximation, a large-scale limit of discrete quantum structures. Layer by layer, the concept of distance has lost its claim to being fundamental. But this does not mean distance is fake. It means distance is effective. It is real in the same way pressure is real or temperature is real. These quantities are not illusions. You can measure them. You can build machines based on them. You can predict outcomes using them. But they are not the deepest description of what exists. They are emergent summaries. Distance may be the geometric summary of deeper relationships, motion relations, curvature relations, entanglement relations, quantum network relations. When you average over enormous numbers of degrees of freedom, when you ignore the microscopic details, the universe presents itself as a vast three-dimensional arena with measurable separations. That picture works. It works astonishingly well, but it may not be the bottom layer of reality. If that is true, then the vast emptiness between galaxies is not fundamental emptiness. It is the large-scale appearance of an underlying structure that does not speak in meters or light years. And that changes how you should see the night sky. So the next time you look up at the night sky and think about the distance to Andromeda, pause for a moment. Yes, in the language of astronomy, it is about 5 million light years away. That number is meaningful. Telescopes, spacecraft trajectories, and cosmological models depend on it. In the classical description, space stretches across unimaginable scales, and galaxies are separated by vast expanses. But now you know that this vastness is layered. The number you quote is tied to light travel time. It depends on how you define distance in an expanding universe. Change the frame of motion, and the measured separation changes. Change the curvature of space-time, and the geometry reshapes. Look at the universe through the lens of quantum mechanics, and spatial separation no longer guarantees independence. Look through the lens of holography, and geometry itself may emerge from entanglement. Look at the smallest scales, and smooth distance may dissolve into discrete quantum structure. Distance survives every test as a powerful and accurate concept. It does not survive as a fundamental one. The universe is not simply a collection of objects scattered across a pre-existing emptiness. It may be better understood as a vast quantum system whose internal relationships give rise to what we perceive as space. What you call separation could be the macroscopic way your perspective organizes deeper patterns of connection. You are not isolated from the stars by light years in the most fundamental sense. You are part of the same underlying quantum structure that gives rise to those stars. The apparent gulf between you and them is the large-scale geometry of a shared reality. The universe is not small, but its depth is not measured only in miles or light years. At the deepest level, there may be no distances at all, only relationships from which distance emerges.